SwayamPrabha. Digital India. Educated India.
In the last lecture, we have discussed how we can come up with the linear model of the force equation in the x direction of the longitudinal motion of the aircraft. So our equation in the x direction, in the longitudinal equation of motion, we had x minus mg sine theta equal to m into u dot plus qw minus rb. And using small perturbation theory, we come up with the linear model of equation d dt minus xu del u minus xw del w plus g del theta cos theta naught and x del e delta del e plus x delta t del t. And this is basically the linear model of the force equation in x direction. This is basically, let me write this equation number 1. So this equation we have already found in the last lecture. So we have gone through the steps to find this expression. Now we'll start how we can find the linear model of the force equation in the z direction in the longitudinal motion. So let me write the force equation in the z direction in longitudinal equation of motion of the aircraft. We can write z plus mg cos theta cos phi equal to m into w dot plus pv minus q. Now we'll proceed the same way what you have done for the x force equation. So we'll here apply the perturbation to the system. So considering, let me write this, let me equation number 2. Considering, okay, this part already have done in the last lecture. And considering forces in z direction and including the perturbation variables. Let me write this variable z equal to z naught plus delta z, theta equal to theta naught plus del theta. So here z naught, theta naught are the reference point or the trim point, and delta z, delta theta are the part of variables. So similarly, we can write for phi naught plus del phi, w equal to w naught plus del w, p equal to p naught plus del p, and V equal to V naught plus del V, Q equal to Q naught plus del Q, and U equal to U naught plus del U. Including these perturbations in equation 2, the equation 2 can be written as Z naught plus del Z plus mg cos theta naught plus del theta and cos phi naught plus del phi equal to m into d dt, w naught plus del w plus p naught plus del p and v naught plus del v minus q naught plus del q into u naught plus del u. So this is the equation which is written in the part of variable form, differential part of variable form. Now, as we know, for the implied condition, again, during stream flight condition, we have P not equal to 0, P not equal to 0, and Q not equal to 0. So rates and the side slip velocity we assume to be 0 in the reference situation or the equilibrium situation, and R net equal to 0 and phi not equal to 0, and del phi also assumed to be 0. Del phi equal to 0 means there is no lateral perturbations in the longitudinal flight. So these are the assumptions. So we are considering for the for finding the linear model of the jet force equation. Now, in the equation, let me write this equation number 3. Equation 3, in equation 3, for small value of del theta, the term, why small value del theta? Because we are going to have this the part of system around the equilibrium point. So this perturbation assumed to be very small. So that's why for the small value of del theta, the term cos theta naught plus del theta yields to be cos theta naught plus del theta. We can write cos theta naught cos del theta minus sin theta naught sin del theta. And again, you can write for this condition, we can write cos theta naught, we can write, so this part we can assume to be 1, and we can write for sin theta, del theta, we can write del theta and sin theta naught. So let me write this equation number 4, and using the condition or equation 4, equation 3 can be reduced to, we can write G naught plus del G plus mg cos theta naught and theta naught minus mg del theta sin theta naught equal to m w dot plus m del w dot minus m u naught del q. So here we have assumed the product of part of variable assumed to be 0, and also we have introduced this condition in the equation 3, and under this assumption the equation number 3 is now reduced to equation 5. Also, what you have done in the previous lecture, that for the trim flight condition, the trim flight condition for the for z direction, for the force equation in z direction yields to be, we have already found, it is basically z naught plus mg cos theta naught equal to m w naught dot. So this is the trim flight condition for the force equation in z direction. Now using this condition, if you substitute this condition equation 5, so equation 5 can be written as, using the above trim condition, we can write equation 5 can be written as, we can write del G minus mg del theta sin theta naught equal to m del double dot minus m u naught del q. So this is the equation number 6. So now, similar to the force equation in the x direction, the ways we followed, the here del z, the part of force, can be caused due to the different variables, and we can write that del z in form of Taylor series. So let me write the force term del z can be expressed by means of a Taylor series in terms of the partition variable. So del z you can write, which is function of, the del z can be caused due to the del u, the part of velocity in x direction, part of velocity in z direction, a rate of change of part of velocity in z direction, and del cube, part of pitch rate, del delta e, and del delta theta, t. So due to this part of variables, the force along z direction may occur. We can write further, if we write in Taylor series form, del z, del u, delta u, plus del z, del w, delta w, plus del z, delta w dot, delta w dot, plus del z, del q, delta q, and plus del z, del delta e, delta e, del e, plus del z, del delta t, delta t. And let me define this equation number 7. Now here we'll replace this variable here, w dot here, in the different form. So let me write here, in the above expression, or in equation 7, del z, del double dot actually represents the rate of change of normal velocity. If you write combine equation 6 and 7, this is for the just for understanding del z, and del how it is going to influence equation number 7. Now, if you combine equations 6 and 7, if we combine equations 6 and 7 yields, we can write m delta w dot minus m u naught delta q plus mg del theta sine theta naught and del z del u delta u minus del c del w delta w minus del z del double dot delta w dot minus del z del q delta q equal to, you can write the elevated and thrust force. So we can write del z, this is the total control, we can write in the right hand side, and del delta e plus del z del delta t del delta. So this is how we can write the expression, the combined equation 7 and 6. Let me define this equation number 8. We'll divide this expression 8 by mass from on both sides of the equation 8. So again, dividing by mass m on both sides, we can write del w dot, delta w dot minus u naught del q plus z del theta sine theta naught 1 upon m del z del u delta u minus 1 upon m del z del w delta w m del G W dot del W dot minus, we can write 1 upon M del G del Q delta Q equal to 1 upon M del G delta delta E delta delta E plus 1 upon M del G delta delta T delta T. So this is equation number 9. This equation further we can write in compact form if we denoting Cu as 1 upon M del G del U and so on for the rest of the derivatives at the aerodynamic derivatives divided by the airplane's mass, we can write the equation 9 can be written as del W dot minus U naught del cube plus G del theta sin theta naught ZU del U minus Z W dot del W dot minus ZQ delta Q U naught delta cube equal to Z delta E delta del E plus, you can write del T. So this is the equation compact form, we write equation number 10. Again, equation 10 can be written as, and write equation further it can be written as minus ZU del U plus 1 minus ZW dot del minus ZW delta W minus ZQ U naught delta Q plus G del theta sin theta naught equal to J delta E delta del E plus Z E. Now, you know that the rate of change of angle, pitch angle, also you can write equivalent to pitch change in the pitch rate. So also you know that. We know that del q equivalent to, we can write del theta dot, and under this condition, the equation, this equation number, equation 11 can be written as the compact form equation, right equation, we can write minus ZU delta U plus 1 minus Z double dot minus ZW delta W minus ZQ plus U naught. Instead of del Q, can write delta theta dot, or we can write del T d dt theta delta theta plus Z delta theta sine theta naught equal to Z delta E plus del T delta T. And further, we can simplify this expression minus, if you simplify this expression, the above expression, you can write ZU delta U plus 1 minus dot d dt ZW delta W minus ZQ plus U naught del T minus G sine theta naught delta theta equal to delta E T, sorry, it is E plus J delta T. So this is also the expression for the force equation along the z direction in longitudinal dynamics, also yields to be linear form. So let me define this equation number 12, linear form. And we started with the nonlinear equation of the force equation along the z direction, and finally came up with the linear form. So this is the nonlinear equation. So using the part of concept of perturbations, small perturbations, we come up with the linear form. So if you notice, this term and this term, this term, this term, this term, these are the terms, basically stability derivatives, and we can find in these terms for a given wind tunnel testing, for a given flight regime or flight condition. And other than these terms, the other variables are arranged in linear form, and hence the system is a linear equation. Our only equation is left is the moment equation along the y-axis, how the moment going to affect the longitudinal motion. So we'll derive the linear form of the moment equation along y-axis in the next lecture. one more thing. So we come up with the linear form of the x and z axis, force along x and z. So once you have the linear form of the moment along the y-axis, then you can combine all the equation and we can come up with the linear state space model. So in the next lecture, we will be discussing how we can come up with the linear state space model of the longitudinal motion of the aircraft.